Rate equations. Rate equation. Link rate to concentration of reactants. Rate equation is rate equals rate constant multiplied by reactant A to the power of its order multiplied by reactant B to the power of its order. Rate is in moles per decimeters cubed per second. Reactants in square brackets as you use concentration. K is the rate constant. Total order for reaction is worked out by adding all reactants orders together. Orders are numbers 0, 1, or 2. 0 means concentration has no effect on rate of reaction, and first order means rate of reaction is directly proportional to concentration, and second order is rate is proportional to concentration of reactant squared. Order isn't the same as stoichiometric values. Rate constant. Rate constant has unit based on overall order of reaction and is found from rate equation. Value of K is independent of concentration and time and constant at fixed temperature. Value of rate constant is at certain temperature and increases if we increase temperature. Rate constant for first order is S to the power of -1. Rate constant for second order is moles per decimeters cubed per second. Rate constant for third order is moles to the power of -2 decimeters to the power of 6 per second. Find rate constant units by rearranging the equation so rate constant is subject, and then insert units and cancel out. Simplify it. Continuous monitoring. This is when you follow an experiment over time and record change in concentration. Gradient is rate of reaction, and reaction is faster at the start where gradient is steeper. Rate drops as reactants are used up and their concentration drops. Then it plateaus and gradient becomes 0, so reaction is stopped. Measure change in volume of gas. Works if there's a change in number of moles of gas in reaction. Using gas syringe for this. Good for measuring continuous rate, but typical gas syringe only measured 100 millimeters of gas, so you don't want reaction to make more than volume. Quantities of reactants need to be calculated carefully. Magnesium and hydrochloric acid make magnesium chloride and hydrogen. Initial rate is rate at the start of reaction where it's fast, and calculate from gradient of continuous monitoring concentration and time when time is 0. Measure initial rate is better because concentration at the start of reaction is known. First, measure 50 centimeters cubed of 1 concentration hydrochloric acid and add to a conical flask. Set up gas syringe. Weight 0.2 grams of magnesium. Add magnesium to conical flask and place bung on it and start the timer. Record volume of hydrogen gas collected every 15 seconds in 3 minutes. Excessive reactants means this reactant doesn't affect rate and is in pseudo-zero order because its concentration stays constant and doesn't affect rate. Comparing continuous rate curve. High temperature, concentration, and surface area means faster rate. If magnesium or marble chip is in excess of acid, then final volume of gas is proportional to amount of moles of acid. Increasing volume means same initial rate, but different final volume. Need to compare initial moles of reactant to know the difference between the volume. Initial rate method. Initial rate calculated from gradient of continuous monitoring concentration over time graph at time 0. Initial rate can be calculated from clock reaction where time taken to reach fixed concentration is measured. Clock reaction has 2 reactions going on. Get in point from when one is limited reactant runs out, so color changes. Hydrogen peroxide reacts with iodide to form iodine, and then thiosulfate reacts with iodine. There's excess iodine in solution, so reaction with starch forms black, blue color. Then experiments done where iodide ions change and concentration is kept the same. In each experiment, the time taken for reaction mixture to turn blue is measured. Repeating experiment while changing the concentration of reactants, you can find order of reaction based on reactants. Initial rate of reaction is 1 over time. Working out order from experimental initial rate data. In experiments, when concentration of one of the reagents is changed and reaction rate measured, you can calculate order using the graph. So, take rate equation, which is rate equals rate constant multiplied by concentration of reagent to the power of its order. then log both sides. So it will be log rate equals log rate constant plus order log reagent concentration. Compare this to straight line equation, which is y equals mx plus c. So the log rate constant is the y-intercept and order is the gradient. High concentration with quick time makes big percentage error. Initial rates can also be in a table. Working out order when two reactant concentrations change simultaneously. If two reactants change, then the effect of both changes on concentration are multiplied together to give overall change on rate. So, say rate was equal to rate constant multiplied by concentration of reactant A in order 1 and reactant B in order 2. If the concentration of A was 2 and the concentration of B was 3, then do 2 multiplied by 3 to the power of 2 to get times 18. So if changes happen at the same time, rate would be times 18. Calculating value of rate constant, also known as K. Calculate the rate constant by picking concentration of reactants from table and the rate, and make sure you use the same experiment values. Then substitute into equation. Then make K the subject and cancel out the units to find value of K and units needed. In graph, when reactant in zero order, the rate stays constant as reactant is used if concentration of reactants has no effect on rate. Rate is gradient of a line, and so is the rate constant the gradient of a line. Effects of temperature on rate constant, the arrhenious equation. Increased temperature increases value of rate constant. Relationship given by arrhenious equation, which is rate constant equals arrhenious constant multiplied by e to the power of minus activation energy in joules per moles divided by gas constant times by temperature in Kelvin. Using arrhenious equation, rearrange it to ln K equals ln AE minus activation energy divided by gas constant multiplied by temperature. Make sure you know how to rearrange and substitute into this. Calculating activation energy graphically from experimental data. Using rearranged arrhenious equation, K is proportional to rate of reaction, so ln K is known ln rate. Plot 1. Over temperature against lane rate to find activation energy. Activation energy equals minus gradient multiplied by gas constant, then divide by 1,000 to get into kilojoules per moles from joules per moles. Use line of best fits, then plot points that fill full graph paper, and then choose points that are far apart on graph to calculate the gradient. Rate equations and mechanisms. Mechanisms are steps that allows reaction to continue. This makes an intermediate compound, and if all steps are added together, they will add up to overall equation for reaction. Each step has different rate, and the slowest step controls overall rate, and this is called the rate determining step. Moles of each substance in the slow step equals the order. Rate determining reaction is based on the equation, so if in the equation you see anything to 0 order, then it's not in the rate determining step. But if it's to 1 order or 2, it is in the rate determining step.